telescopes. So the next talk is also quite exciting, and there are new results, and some of them were reported also during the COSPAR. So the advance in energetical particle physics with the solar orbiter, and the talk was given by Robert Wimmer Schweingruber. Okay, and the floor is yours, and I'll give you 5 minutes.
I'll give you a 5-minute warning. Okay, good morning. Thanks a lot for the invitation. Of course, what I'm going to talk about is not only my work, it's also the work of our PI, Javier Rodriguez Pacheco, George Ho, and the entire Solar Orbiter team, and also the EPD team, and many, many other people around the world. Solar Orbiter was launched back in February 2020. Everything worked fine. It was just before the corona wave hit the Western world, but I'm not going to talk about that. So the idea is that with Solar Orbiter, we want to study how the sun creates and controls the heliosphere. That's this giant bubble that is inflated in the interstellar medium by the solar wind. And then also how why and how solar activity changes with time. So basically to understand the dynamo of the sun. We don't really understand the dynamo either. And that can be broken down into these 4 different, more detailed questions. What drives the solar wind, and where does the coronal magnetic field originate? How do solar transient drive heliospheric variability? This is what I will focus on. How do solar eruptions produce energetic particle radiation that fills the heliosphere? That's what the energetic particle detector does. And then finally, to understand the solar dynamo. It was launched, as I said, back in February, 10th of February. Mission duration is 7 years, nominal mission duration, 3 years extended. You can see basically here the orbit. It orbits the sun. Yes, we start at 1 AU because we launched from Earth. We dropped into the inner heliosphere, then came out again. In we go again, out, in, out. And then we reach at some point about 0.28 astronomical units perihelion. And we also go to high latitudes to understand the dynamo up to latitudes of about 34 degrees. Solar Orbiter is not just one instrument. We heard a lot about AMS or other big instruments. Solar Orbiter consists of 10 instruments, which each instrument has different sensors. So there's about 40 or 50 boxes, which are parts of instruments on Solar Orbiter, and they're distributed, as you can see here. We have a solar wind instrument, the electrons at the very back of a boom. We have a lot of optical instruments. There are 6 optical instruments and 4 in situ instruments. And as I said, we will be talking about the energetic particle instrument to understand how the sun produces these solar eruptions that produce energetic particle radiation that fills the heliosphere. It's also a way of trying to understand how are these high energy particles actually accelerated, which of course is something that's at the center of this conference as well. So we can break this question into 3 sub-questions. One is we need to understand the solar energetic particle, SEP, seed populations. We need to understand the injection, acceleration, and release processes of these SEPs. And we need to understand SEP transport, that is how these particles get to us. They're bound somehow by magnetic field lines, and they need to get to us. So there are a number of populations of energetic particles or of particles in the heliosphere. One that we've been talking a lot about are galactic cosmic rays, which come from outside the heliosphere. And at the totally different energy end of the energy range, we have the solar wind at an energy of typically about 1 keV per nucleon. That's 440 kilometers a second. In between, we have some other particle populations, as I said already, solar energetic particles, which are accelerated somewhere close to the sun. particles which are accelerated at co-rotating interaction regions, that they drive shocks, which can then accelerate particles. Coronal mass ejections that we just heard about from Ed can also accelerate particles to high energies. And then there's another interesting component that is due to interstellar neutral gas, which enters the heliosphere as a neutral gas population, is ionized, picked up by the solar wind. In the frame of the solar wind, it rotates around the magnetic field at the solar wind speed. And so in an observer's or sitting observer's field of frame of reference, it has about twice the solar wind speed. Now that means that these are superthermal particles which are especially well accelerated at shocks, because you need a large delta V to be accelerated efficiently at shocks. And that means that when these particles, although they cool and everything on the way out to the termination shock, they are very efficiently accelerated at the termination shock, and then they return as so-called anomalous cosmic rays, as which we can measure them then inside the heliosphere. And so then this is the energy distribution. You have the solar wind here at typically about 1 keV per nucleon. We have galactic cosmic rays here at around 300 MeV per nuc. And they extend all the way up, and you guys know a lot more about what happens down in this corner, I'll say down in this corner, with all the structures of the lower extremities. But what I'm going to talk about is this region here, because this is where these particles are injected into the acceleration process. Here now I somehow... Yeah, so what I'm showing here is energy and differential flux. And up here I have sunspot number. And you see that the differential flux varies a lot in this energy range between about 100 keV and about 10 MeV. During solar activity minimum here, you'll see that this drops down to very low levels. There's not very much going on here. And then during solar activity maximum, which of course the last maximum was kind of wimpy, you see that this increases quite a bit. Whereas the galactic cosmic rays, which we have been talking about, and people were very excited about the variations in here, were very, very small. Okay, so I've summarized the variability right here, and you can see that there's quite a bit of variability, about 6 orders of magnitude in variability. And that tells us there's a lot going on there. The reason for this discrepancy here is simply due to a malfunction of the ULICE instrument on ACE. One of the time of flights broke down after a while, and that means that during quiet times, it doesn't measure the spectrum correctly at the highest energy. So this is where the energetic particle detector then actually measures. So roughly from a few keV up to a few hundred MeV. So I don't know whether Charlotte is here, but you wanted measurements above 100 MeV. And yes, we do have these measurements. They are provided by Solar Orbiter EPD. So what do we need to do? Well, to understand the seed population, injection, acceleration, and release processes, and SCP transport, we need to get close to the sun. We need comprehensive energetic particle instrumentation, which we have with EPD. We need a broad energy range. We go from a few keV up to a few hundred MeV. And we need composition, because different composition means different rigidities, because the charge states vary. So we also need superthermal particles. I think I just showed that a moment ago. We need high time resolution. I'm not going to go into too much detail about this, but some of the high time resolution data that we have now are just absolutely incredible and very astonishing. But that's something that we're just preparing right now. We need directional pitch angle information. And of course, Solar Orbiter is an observatory. We have 10 instruments. I'm not only going to talk about EPD, but also about the other instruments. We need supplementary remote sensing measurements. So this is EPD. I'll briefly describe EPD and then I'll come to the results. We have 4 instruments in EPD, the superthermal electron-proton instrument. We have 4 instruments. We don't give individual particles a name, but we give our instruments a name, and we affectionately give them names like STEP and EPT or HET and CIS, so it's not very, very romantic. We have the energetic particle, the Electron-Proton Telescope, the high-energy telescope. This is the high-energy telescope. This is the Electron-Proton Telescope, and we have 2 of them. And we have the superthermal ion spectrograph, which are all linked up to one instrument control unit, ICU, which is the only interface with the spacecraft. We have 4 instruments. STEP points in one direction. That's given by this blue rectangle here. There are 15 pixels in this, so it's kind of a pinhole camera, as I'll show in just a moment. EPT, that's the red circle here. That's one of the fields of view. It's a bidirectional telescope, so we have 4 different fields of view. The same is true for HET. They're co-aligned. HET, the high-energy telescope, has a slightly wider field of view, and CIS has a fairly narrow field of view. This is in a Mollweide projection. You have the sun here at the center. The color code is the direction of the magnetic field as it was measured with Helios more than 3 decades ago. So red here means this is where we expect to see most of the solar wind of the magnetic field direction to come from, because the particles coming from the sun, they will spiral along the field, and the first to arrive will be those with the smallest pitch angle, so they will be flowing directly along the magnetic field. So that's the reason for this arrangement of the viewing angles. As I already said, we cover a wide energy range. STEP is the red here. It goes from about 2.5 keV electrons up to about 100 keV electrons. Protons, we need a slightly more energy to penetrate the dead layer, goes up to about 100 keV. We have quite a bit of overlap with the Electron-Proton Telescope for ions and for electrons. And then also some overlap with the high-energy telescope, which goes to about 15 or 20 MeV electrons, and protons up to about 100 MeV, plus 3 more bands up here, which I will explain in just a moment. Then CIS does a lot of composition. It does helium isotopes, CNO, neon magnesium silicon, so it resolves the elements all the way up to iron, and the same for HET. The gap here is due to funding difficulties in one of our partner institutes, but that's the way it is. So the STEP instrument, as I said, is basically a pinhole. We have 2 pinholes or 2 apertures pointing towards the sun. You can barely make out the aperture right here. This is a magnet system in which we deflect the electrons. So we can measure ions in one telescope, and we measure the sum of ions and electrons in the other telescope. And by taking the difference, we can plot either electrons or ions. We have 15 different pixels behind the pinhole. So we have quite a bit of directional information. And this is shown right here. This shows part of the variability. These are a few hours of data picked for November in 2020. These are these 15 pixels. And you see that in this pixel, which is actually pointing down beneath the ecliptic plane, you see lots of low energy particles here, whereas in the pixel pointing above that, you see hardly any particles. You see a lot of action here in the middle pixels. You see action over here towards the end of the time period, which you don't see here. And this is all in a very, very narrow field of view. So this is actually remarkable. We can do this at much better time resolution. So we can take one of these interesting time periods and zoom in to a cadence of about 1 second. This is brand new that we can do that, and I hope to be able to report on that some other time. The Electron-Proton Telescope is actually also an electron-ion telescope. It also uses magnets to deflect electrons and a foil to stop ions. in the two telescopes. We can measure all the way up to about 7 MeV with it for ions, or 7 MeV per nuc for ions, not only for protons. And in fact, we can use this if we have an energy deposition which is larger than about 7 MeV, then we know it has to be an alpha particle. And that can actually be used to measure alpha, even the alpha isotopes with this electron-proton telescope. But of course, the isotopes are much better measured with CIS, the superthermal ion spectrograph. You see here helium-3 and helium-4. The resolution is absolutely incredible. It's a time of flight or multiple time of flight instrument with a cadence of normally 30 seconds, best is about 3 seconds. Goes all the way up to about 20 MeV per nuc, with a large geometry factor, which is variable so that we can account for times when the sun is very, very active. The high energy telescope is summarized right here. Basically, it's 3 detectors and a BGO scintillator acting as a colorimeter. It's about 2 centimeters thick, so it stops 100 MeV protons. Then there's another detector here at the back as a veto, and the whole arrangement is mirrored so that we can do forward-backward measurements. And we can, of course, also measure particles that penetrate the whole stack, and that's what's shown here, where we have protons, alphas, the heavy elements here. This is a projection along the axis here, so of the fully penetrating particles. So this is the galactic cosmic ray composition, which we can do. It takes quite a long time because this is a small instrument. We're not talking about AMS. We're talking about something about this size, you know, about a, well, 20 by 20 by 20 centimeters. So these are tiny instruments compared to what you guys are used to, but we don't need large instruments because, as you saw, the flux is a lot larger. We can combine instruments, of course. This is a time period I'll be talking about in a moment, but you can see here nicely the helium. This is solar helium here. This is a mixture of anomalous cosmic ray helium and of galactic cosmic ray helium. And here we have some data points all the way out to about a giga-electron volt and around 200 and 300 MeV. But we have very, very good energy resolution at lower energies. So, solar orbiter, we orbit the sun, but it's not only us who orbits the sun, there are also other spacecraft who orbit the sun. I like to call that the Grand Heliospheric Observatory. And now it doesn't work, which is a pity. It was supposed to work. Well, I'll leave that out. Basically, we also have Parker Solar Probe. We have stereo, we have Bepi-Colombo, and we have all the near-Earth assets. So we have at least 5 points in the heliosphere at which we can measure these solar particle events. So we can do multi-point measurements in the heliosphere, which has turned out to be enormous in the consequences, because we can now find out what particle transport does, where are particles accelerated, how well are they accelerated, does it depend a lot on the shock, on the geometry, and so on. So these are things which we can now do, which weren't possible about 3 decades ago. That started with stereo especially, but now, of course, with more than 5 data points in the heliosphere, this is getting a lot better. So here are some data. You see EPD data from Solar Orbiter, March to May 2021 down here. This is energy and this is time, and I don't expect you to see everything. All I want you to see is that, yes, we have some low energy superthermal stuff bubbling around here, and we have some injections here. These are ion injections. These are events from the sun which accelerated ions all the way up to about 100 MeV. And we have the same for electrons here. So we have a nice clear electron event here. This is mainly due to contamination here, but I'll be talking about that later. So that was in 2021, and 2022, well, the sun has woken up. So we're approaching, or we're going up into solar maximum now, solar activity maximum, and you see that the situation has changed a lot. So I'll be reporting first results. There's a special issue of Astronomy and Astrophysics out. It was published end of last year, issue 656. There are 53 papers, of which 16 use EPD data. The talk is uploaded or has been uploaded. This is an active link. You can click on it and you'll find links to all the 53 papers, which are all open access, so everybody should be able to read them. One paper basically expands on the instrument paper of EPD. We take an example, which is in late 2020, in December 2020, which I'll be briefly talking about. And we have studied one other event in July 2020, which we used to cross-calibrate the various sensors inside the EPD detector. So this is a December event. It's not really spectacular, but it's a very nice event to showcase the capabilities of EPD. You see this nice event now at our energies, MeV per nuke for ions. We see what we call velocity dispersion. Low energy means low speed. Now, for you guys, low energy is in the GeV or TeV energy range. For us, that means MeV or KeV. And so we actually do, it's not all the speed of light. So that's a theoretical curve here, what we would expect based on just simply energy. Well, energy and velocity belong together. And so you can see very nicely that this event follows that. There may be something very weak here as well, which we'll talk about in a moment. You see the same for electrons as well. This was ions and this was electrons here. We do have some problem with contamination by high energy ions, but because electrons at the same energy are a lot faster because they're lighter than ions, they arrive first and the ion contamination arrives later. The curves down here are the different telescopes of EPD, sunward, anti-sun, north and south. And you can see that this event here was very anisotropic. So basically, these telescopes didn't really see anything. These telescopes saw something, and there's a factor of 10 between in the intensity, and the same for electrons, very anisotropic event, which you can see here in this pitch angle plot. So you have pitch angle here, 90 degrees pitch angle, 180 degrees pitch angle. So this is where the particles were coming from, streaming straight from the sun at solar orbiter. We've plotted that right here as well with pitch angle here and intensity along this axis going from low intensity to high intensity. And here you can see the electrons measured with step with the 15 pixels of step overlaid with the EPT pixel here at this first time instance right here. And you can see that we have very, very nice measurements of the very fine pitch angle distribution. Of course, we don't only have ion measurements as ions, but we know which ion it is. These are the cis measurements right here. These are the measurements we just took a look at. These were all we could say these are ions, but we can actually see it's helium, mainly helium-4 here, but there's also carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, calcium, and iron. And if you look carefully, you see some velocity dispersion right here, which is earlier than this large event. And the reason for that is that the cis spectrograph has a much lower noise because it uses multiple time of flight. It's a multiple coincidence instrument. And so you can see this earlier injection. And if you look very careful, you see a very faint trace here, and that's probably exactly this. Now, using the composition from cis, we can also understand what's going on in EPT. So what the contribution is of heavy elements to the EPT measurements. And that's what we did here in the left-hand panel. We see the measurements of EPT, that's the blue dots here, and the measurements of cis. And we basically added up all of cis measurements to obtain the EPT measurements. And basically, so that tells us, yes, of course, there is a contribution of heavy ions to the measurements in the Electron-Proton Telescope. And that doesn't go with the normal abundance, because we measure total energy in EPT. And if the particles all have the same slope in energy per mass, it'll depend on the shape of the spectrum, and there will be a large contribution, which can be on the order of 50% or even 1-to-1 of heavy elements in the measurements of EPT. And that's what's basically highlighted in this figure. Now, Alex Kolhoff looked at a different event. That's this largest event that we had in the first year of operation in December or November, at the end of November 2020, where we see measurements here at Solar Orbiter with EPT and HET, at Parker Solar Probe. So the event was seen at Parker Solar Probe as well. It was seen at Stereo, which was at this longitude, and it was also seen at Earth. The CME or the flare took off this direction, so that's the nominally best connection here in black. And you see that all 4 spacecraft, which were very widely separated, about 230 degrees separation, they all measured this particle event, which, well, it's nothing new. We know that that happens, but it tells us something about what's going on at the sun. And some of the ideas about what's going on at the sun is that you have these waves driven by, we call them EUV waves, because they're visible in the extreme ultraviolet, which are driven by the eruption at the sun. It drives a shock wave, which goes around the sun, and this shock wave then accelerates the particle, or the particles. Now, it turns out that this can't explain the observations. The onset of the particles are too late compared to this wave. So there must be some other mechanism doing that, and that's something that is discussed in this Kolhoff et al. Paper. One of the things that influences the particles on their way to the observer is the turbulence in the plasma. It's also important for accelerating the particles, especially the superthermal particles. And so it's also interesting to study the evolution of turbulence between the inner heliosphere and the outer heliosphere. So what happens with it? It hasn't been possible to do that often. It was done a little bit with Helios, but here for the first time we had the opportunity, due to a lineup in September 2020, when Parker Solar Probe was at about 0.1 astronomical units. So just about at the Alphanic surface for the solar wind. And Solar Orbiter was just about at 1 astronomical unit. And so we could follow the same solar wind parcel or plasma parcel from Parker Solar Probe all the way out to Solar Orbiter. So these are the measurements at Parker Solar Probe. You see quite a bit. These are magnetic field measurements, and you see that there's a lot of fluctuations. So you have a strength of, let's say, minus 200 nanotesla here, and fluctuations on the order of, well, delta B over B, about unity. So that's very, very turbulent. At Solar Orbiter, during the same time period, you see that a lot of the turbulence has disappeared, and I'll just flicker between the two for a moment so that you can appreciate just that the plasma has evolved quite a bit. Now, this time period, which is singled out here, that's what we believe is the same plasma parcel. And for this plasma parcel, what Deloni et al. Did in a paper reported in APJ was to study the turbulence in a lot of detail, and these are the results. So basically you find for the trace of delta B squared that it has changed quite a bit from Parker Solar Probe to Solar Orbiter. It is roughly a minus 1.5 slope here, which means it's highly alphenic, it's hardly turbulent, to approximately a Kolmogorov spectrum right here with a break at around 0.2 hertz, which is the gyro period in the inner heliosphere. So this means that we have highly developed turbulence already, and basically the same is seen in compressibility as well. So in summary, we see highly alphenic fluctuations in the inner heliosphere, less developed turbulence, and at 1 AU already we see fully developed intermittent turbulence. Now this tells us that Solar Orbiter is doing exactly the right stuff by scanning the stuff in between, because that gives us a way of understanding how turbulence evolves from the sun all the way to 1 AU, where turbulence is already fully developed. Another way to probe that is using heavy ions. Heavy ions, they have a different charge to mass ratio than protons or electrons. And so by looking at their spectra and their spectral breakpoints, you can actually study the evolution of turbulence throughout the heliosphere as well. And that's something that was studied by Glenn Mason. Basically, that would be the subtitle of his talk, Heavy Ions as Tracers of the Acceleration Process. Raúl Gómez Herrero studied 5 events, which you see here. They're near-relativistic solar electron events. So yes, we do have relativistic particles as well. Electrons, we measure them up to 20 MeV, and they're highly relativistic, but in this case, we're only looking at them up to a few hundred keV, so they're near relativistic. We had several electron injections here in this period in July of 2020. That was close to perihelion. So perihelion was right here, and we're talking about these events right here, where even for electrons, we saw substantial anisotropy in these electron events. Now, this doesn't look like that. These are the measurements in the various sensors, EPT sensors here, sun, anti-sun, north and south. This is the pitch angle, and this is the pitch angle, but now color-coded with intensity. And you see this weird pattern. And this was a fantastic opportunity for us to cross-calibrate the different sensors, because that's when the spacecraft did a roll to calibrate the magnetometer. So it rolled 8 times around its axis, which points at the sun, and that's what shows you these, well, it looks like fluctuations, but it's actually a systematic roll at an exactly constant roll speed, and that gives us the opportunity to intercalibrate the different EPT sensors. Nevertheless, you can make out, yes, there was quite a bit of anisotropy right here. So this was a highly beamed electron event, very similar to this event, the 5th event here, which was also highly beamed, which you see right here. And in fact, there were multiple injections, and that's one of the new capabilities of EPT and STEP on Solar Orbiter, is because we have this very high time resolution of up to 1 second now, and excellent energy resolution, we can measure the velocity dispersion of these particles and then map them back to the sun and determine when these particles were released at the sun. So basically what's shown here is the speed of light divided by the speed of the particles, and in this case of electrons, and this matches very, very nicely with the radio signatures which are measured by the radio and plasma wave experiment on solar orbiters. So these particles here, they were accelerated close to the sun in the upper corona, where they emitted radio waves, which are measured by solar orbiter as well. And then later on, we measure the electrons themselves. That we measure them themselves is also shown in this purple line here. These are measurements at the local plasma frequency, and you can see that they line up very, very nicely with the time when the electrons arrive at solar orbiter. I'll skip this and move on to Radoslav Vucic's paper, which looks at the events just preceding this large event here in November. They were interesting because they were very rich in helium-3. Now, helium-3 is released in impulsive solar particle events. You can see that there's quite a bit of helium-3 right here. So what we show here is the mass measured with cis and time in this direction. And you see at a mass of 3 atomic mass units and 4 atomic mass units, these are the helium isotopes. Helium-3 is typically about 2,500 times rarer than helium-4. On Earth, we have hardly any of it or none at all. In the sun, there is a little bit, about 2,500 times less than helium-4. But occasionally, you see here, there's about as much or even more helium-3 than helium-4. And that tells us something about the acceleration process that is going on there. There are various theories for that, but we believe that we'll be able to lock in on this also because we now have all these measurements, detailed measurements of the heavy ions and the composition of the heavy ions. Glenn Mason looked at some of these events during the first perihelion passage, and you just see the excellent resolution here of helium-3 and helium-4, so they're very well separated. The ratio here was about 0.6. If you look at the time series here, you see blue and black. Blue is helium-4 and black is helium-3. So basically at the onset of the particle event, you had the same amount of helium-3 as helium-4, and then later on you have less. But still, it's maybe a factor of 3 or 4 less, and not a factor of 2,500. The resolution again is shown here, and that's for something which is only about this size. This is really, really good. So we're really proud of that, and it's working very well. We can measure spectra of these particles, energy spectra. We have MeV per nuc here, fluents, and you see the helium-3 and helium-4 in red and blue. They have the same spectral index, but here at the low energy range, of course, they start to differ. Now the question is, how are these particles accelerated and how are they injected, and what is a superthermal particle population? And that's one of the things I'll do in the last few slides. I'll take a look at the last few slides. So Glenn also studied or investigated one of the ideas is that there's a remnant flare population, that there are particles which are accelerated in flares, and they just sort of diffuse around in the inner heliosphere. They hang around, and when a shock passes them, then they're accelerated very efficiently, and then we can measure them wherever we want to measure them. So the idea was to look at really, really quiet times, and what Glenn did was to look at these time periods A, B, and C here. You see particle intensities in blue and red for protons and helium. And during these really quiet time periods here, there's basically hardly anything that was measured. And of this basically hardly anything, that's the spectra which we looked at for the quietest 192 hours. And the other hours are basically shown over here. And so the point is that yes, you still do have superthermal protons, helium, oxygen, although for oxygen and iron, it's mainly upper limits that we can give. And of course, galactic cosmic rays, or the low energy galactic cosmic rays, they're still around as you would expect. But yes, there is this kind of superthermal particle population. In the interest of time, I will skip this. No, I'm not going to skip this talk, because this again tells us something about the local acceleration of particles. So Ángel Arán looked at an interesting event which happened close to perihelion as well in June 2020. It's a strong ion event, no electrons. And what's interesting is that it was inside a CME. So we saw basically a 4-Bush decrease. These are the count rates in the high energy particles, and they drop. Whereas the particles at low energies, they're increased at a shock. So this is a clear indication that we have very, very local ion acceleration in this region. And that was then further studied also by Rob Allen with CIS, who looked at acceleration at correlating interaction regions. These are the 6 interaction regions which he studied. and basically you find very clearly a local acceleration. It's not as much as has been seen previously. This is a measurement of 22 CIRs at 1 astronomical unit with ACE ULIs. What we see for one of these CIRs here, basically for CIR 1, this CIR right here, these are the spectra at solar orbiter in blue, at 1 astronomical unit at ACE. Now you may wonder, why the hell do we see more at ACE? Well, co-rotating interaction regions are large structures which are driven by the fast solar wind running into the slow solar wind. They form shocks beyond 1 astronomical unit at around 2 or 3 astronomical units. And these are particles which are diffusing back inside the into the solar system, into the heliosphere. And so what we see here is that we see more at ACE and less at solar orbiter, because they need to go farther in to get to solar orbiter. And that again means that we have a handle on the diffusion coefficients, or the diffusion properties in the solar wind between where these particles were accelerated and solar orbiter's position. And that's basically summarized here. It's a result which has been known for a long, long time, but we've managed now to show that we measure the same in this solar cycle as were measured by Van Hollebeke more than 40 years ago. That was the other golden time in space exploration, when there were multiple spacecraft flying through the solar system. Now, I want to stop this talk with something which apparently doesn't have much to do with energetic particles, and that is observations of extreme EUV, quiet sun brightenings observed by the extreme ultraviolet imager on solar orbiter as well. So what we see here is an image of the sun taken with the full sun imager of EUI. And in that, there's also a higher resolution telescope, which is shown by the white circle, which is expanded here. And in there, we're going to look at this region, which we see right here. And in here, we'll study this red circle. And if you look at it very carefully, you will see a tiny little brightening. Doesn't sound very interesting, does it? Now, what makes it interesting is the following. This brightening, as many, 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 many others, could be studied with solar orbiter at one location, and with the Solar Dynamics Observatory Atmospheric Imager Assembly, AIA, from 2 different points of view. And that means that you can do triangulation, and you can determine the height above the solar surface of these brightenings. And that's never been possible before, because we always had observations from the same location. So now we know, now we can do the 3-dimensional structure of these little loops. And these are tiny loops. Some of you may see where I'm getting at. So you can study the height of these tiny loops. And if you had a semicircular loop, you would expect this black line here. This is the length of the loop, and this is the height of the loop. So you would expect this black line. And what is measured? Well, these are 16 of a few hundreds or thousands of such loops, which were especially well studied. And we see that obviously they're not semicircles, so they must be elongated. So they're elongated in height. They're also basically concentrated along the chromospheric network. So the foot points are in the chromospheric network. And the size distribution is given right here. So you have the total intensity in photons. You have duration of these loops, and you see that, well, we're limited to 5 seconds here. That's the cadence of EUI. So basically what David did is take only events which he saw in at least 2 exposures. So there were about 2 hours worth of data. So it goes out to not quite 200, maybe 140 seconds. So basically the duration is also a power law, and the probability density of seeing these pixels, such pixels per megameter squared, is given here, and this too is a power law. So basically, and that's the new thing, is these small eruptive events on the sun, previously they were known to exist and to have a power law somewhere. I would have to show it somewhere down in this corner. These are flares, micro flares, mini flares, and so on. But what we're seeing now is this idea that Parker had about nanoflares. So these nanoflares exist. This is the first conclusive proof that these nanoflares exist. And they're important to heat the solar wind. They're important to heat the corona. The energy budget is here. And now we found out where the energy budget is going to heat the corona. So basically, this is the distribution. They're slightly hotter than the average of the low corona, and they're a little bit brighter, of course, but that's not that important. So, in summary, we've launched. The science is starting to pour out. We have this first special issue of first results that I reported about. I reported a few papers out of 53. There's many other publications. We have next ANA special issue with a due date in December 2022. So we all know what to do in fall. If you want to use data, the data are freely available 90 days after receipt on the ground, very often earlier. We're doing our best to have a fully open data policy. You can find the data here. Again, this is an active link. The future is multi-point. So it's not only one observation, but many multi-observations. We're part of a grand heliospheric observatory. The inner heliosphere is exciting. We can measure now the seed population, the injection mechanisms, acceleration mechanisms, and transport all in action. And here, just to summarize this, this is the Solar Orbiter Archive. You can download the data here. You can play with the data. They're available at the latest 90 days after receipt on the ground, and we do monthly updates. With this, I'd like to thank ESA, especially European taxpayers, NASA, the German Ministry for Economic Affairs and Energy, the Spanish equivalent of that, all of you for listening to me, and especially Jörg and his team for organizing this really fantastic and impeccably organized conference. Thank you.